computer. Okay. Welcome back, everyone. This is the 2024 virtual residency workshop. It's day one, Monday, June 24th, 2024. And this is the second talk, Effective Communication. And let's dive right in. I'm Henry Neiman. Let's go get started. So here's a quick outline. We're going to talk about how to talk to researchers, and particularly about research terminology. Then we're going to talk about, as promised, about enterprise IT versus research computing. We'll talk about the mindset gap. We've already touched on that a little bit. Types of researchers, what to say to a researcher, how to find researchers, and how to find their projects. Okay, so how do we talk to researchers? So, is oxygen a metal? So let's do this by show of hands. How many of you believe that oxygen is a metal? Just do like the hand up thing. Um, by show of hands, how many of you think, yes, absolutely, oxygen is a metal? I got 3, 4, 5 hands raised out of 154 people. 6, 7 hands raised about 150 out of 154 people. Okay. Oh, and somebody who can't make up their mind. So it could be, and it's going down now. People are changing their minds. Maybe they don't think that oxygen is a metal, but almost nobody here believes that oxygen is a metal. Okay. So what is oxygen? Well, in yeah, and by the way, you can lower your hands now because I keep getting these little notifications about them. Um, so in real life, what's oxygen? Atomic number 8. It's what they call a chalcogen. I don't know what the heck that is. I'm not a chemist. My dad was, but I didn't learn a thing from him. It's a key element in life. If you don't have oxygen, you die. It's also a key element in fire and rust, and you can't make water without oxygen, and on and on and on. Oxygen, we all agree, is super duper important, but it does not seem to be a metal, at least to most of us, right? But what if you are an astronomer? In fact, what if you are like my grad advisor who is a cosmologist? So he studies the entire universe over its entire life, 14 some billion years is the best estimate. Okay. What if you're a cosmologist or more broadly an astronomer? What's the universe made of? Well, we don't know what dark matter is. Yeah, we're going to get to that, Anton. That's a very good point about the under high pressures, oxygen starts acting like a metal. In fact, most elements do. So, in the visible matter of the universe, hydrogen is the number one ingredient for the visible matter of the universe. We don't know what dark matter is, but the visible matter of the universe, 75% of all baryonic mass. I don't know what the word baryonic means. I'm pretty sure I understand what the word mass means. And most stars are made of hydrogen, right? Hydrogen plasma. The number 2 ingredient to build our universe is helium. Helium is atomic number 2. It's noble gas, and it's 24% of total elemental mass, whatever. I don't know the difference between elemental mass and baryonic. I don't know what any of that stuff means. Doesn't matter. Basically, 99% of the universe is hydrogen and helium. And everything else is 1% of visible matter. Okay. What are planets made of? Well, they're made of metals in the chemical sense, right? Actual metals on the periodic table. When we say metals, we generally mean they're hard and they're shiny. But there's a more specific chemical definition. So the core of a planet typically is going to be stuff like iron and nickel. Like Earth's core is almost 90% iron, 6%, so 89% iron, 6% nickel, 5% anything else. The mantles are not, right? The outer crust is not metal, but the innards of a planet are metal. And as Anton mentioned, when under high pressure, like in a star, elements other than hydrogen and helium start to behave kind of the way metals behave. So if you're a chemist, the word metal means something very specific. And in this diagram here, it's all the yellow bits. All the yellow bits are metals. All the orange bits are semi-metals, whatever the heck that means. And all the green bits are not metals, including hydrogen, helium, and oxygen. But to an astronomer, and especially to a cosmologist, anything that isn't hydrogen or helium is a metal. So the notion of metals to an astronomer, especially a cosmologist, is anything that isn't the core ingredients, pardon the pun, the key ingredients of the universe, the dominant ingredients of the universe are metals. Now, when I was in grad school and I was hanging around with these cosmologists, it took me 3 years to pick up on this, 3 years to realize that when they said metals, they did not mean hard, shiny things. They meant other than hydrogen or helium. That was a huge revelation for me 3 years in to realize that that's what they meant when they said metals. What's projection? If I take a mathematician, a psychologist, and a movie producer, and I sit them down at a table together, and I say, agree on what projection is, what's going to happen? What is projection to a mathematician? To a mathematician, projection means taking something from a higher order space, like three-dimensional, down to a lower order space, like two-dimensional. So if you've ever seen that picture of two squares with four diagonal lines connecting their corners, that's not a cube. That's a 2D projection of a cube. And if you've ever seen a picture of a tesseract, which is a four-dimensional hypercube, it looks like a cube inside another cube with the corners connected. But that's a two-dimensional projection of a three-dimensional projection of a four-dimensional object. Projection means take something from a higher order space to a lower order space. What does projection mean to a psychologist? It means imposing what you experience on others. Oh, you're lying, because that's what you'd be doing in that circumstance. What's projection mean to a movie producer? And this actually has some relationship in a weird way to the mathematical definition. So a movie producer, when they say projection, they mean shining a very bright light through celluloid 24 times a second in order to put an image on a screen far away. That's what they mean by projection. So they're never going to agree on what that word means. So a key skill that you develop, but only by experience. Most people aren't born with this skill. How to tell when people are talking past each other. I have a colleague, I love this person to death. They're a wonderful person. I enjoy working with them, but I can't have a conversation with them without talking past each other. I'll say, I'm feeling kind of blue today. And they'll say, oh, I agree. The sky is totally blue. Right? That's not literally the conversation, but it functions that way. Right? We talk past each other because we're using the same words to mean completely different things, and sometimes different words to mean the same things. Right? If you ever want to see a fun version of this, watch the famous Who's on First sketch from Abbott and Costello from I think it's the 1930s or 40s, where one of them is using words like who and what to mean the names of baseball players, and the other thinks they're the regular words. What's a fluid? Well, we normally think of the word fluid as meaning a liquid, right? So what's a fluid? Is a fluid a liquid? Well, that's mom's definition. That's your doctor's definition. Drink plenty of fluids, right? That's what you do when you catch a cold. You drink plenty of fluids, right? Wonderful advice that you got. But in physical science and engineering, fluid means not a solid. And liquid is a kind of fluid, but so is gas. A gas is a fluid. Liquid is an incompressible fluid. And in fact, the most common kinds of fluids in science and engineering, physical science and engineering, are gases, right? So the most commonly studied fluid in fluid dynamics is the atmosphere of the Earth. Either because, for example, you're a meteorologist studying weather processes to try and predict what the weather's going to be, or you're an aerospace engineer studying airflow over a wing foil so that you know how to get enough lift in the wing of the aircraft, right? So the physical scientists and engineers don't agree with mom and the physician about what a fluid is. On the other hand, in social science, something that has room for interpretation, for example, gender, can be said to be fluid. A feeling or a mood or an appearance can be said to have to be fluid. In finance, an asset that's convertible to cash is fluid. So depending on the context, and by the way, social science is pretty big. There may be within social science disciplines and subdisciplines and sub-subdisciplines where fluid means something else again, something entirely different. What's the database? Well, as a computer scientist, I was trained as a computer scientist. To me, database means like SQL or Oracle or Access or whatever, right? Has a very specific set of characteristics. But to a bioscientist, they use the word database to mean a large collection of flat files. To me, as a computer scientist, that's totally not a database, but to them, that's a database. And when I talk with bioscientists or with people whose discipline I don't know, and the word database comes up, I ask that question. Which of these do you mean? Usually, they can answer. Sometimes they don't even understand why I would ask such a question because they're so familiar with their definition of database that they're not even aware that there's another definition. So the question doesn't make sense, right? Fish don't know that they swim in water. What's the difference between data and metadata, right? What is metadata? Metadata is data that describes data, right? So, for example, now in your data management plan, if you write grant proposals in your data management plan, you have to say, well, where am I going to put the metadata? Where am I going to put the data? Right? What about code? If I write some code, if I write a program, I write some software, is that data or is that software? Well, it's data to the person who wrote the compiler or the interpreter for the programming language that I'm using. Then it's data. On the other hand, to the person running it, it's code. How does scale impact this? If I'm studying molecular dynamics, or I'm down to quantum scale even, right? I'm studying quarks or whatever. And my time scales are femtoseconds for the entire experiment. The whole experiment takes up a simulated femtosecond, right? The individual ticks of the clock are attoseconds or whatever is smaller than attoseconds. I can't remember. Then how important is gravity? For subatomic particles, for quantum scale, over tiny, tiny time increments, how much does gravity matter? But on the other hand, what if I am a cosmologist studying the entire universe over billions of years? Then how much does gravity matter? Arguably, at that point, it's the most important thing. But for the quantum scale question, it may be the least important thing. So this raises a question. And look in the Google Doc and add to it. Add to the Google Doc. What are some disciplines where gravity does matter? And what are some disciplines where gravity doesn't matter? Anybody want to throw some in the chat or shout them out? What's a discipline where gravity does matter? Everybody's being shy. Physics. In physics, gravity matters. Well, which physics? Because in astronomy, certainly gravity matters. How much does it matter in high energy physics? Horst, I think you're probably still on the call. If Horst is on the call, he can answer that question. Oh, here's
Yeah,
a good
I
one.
think it's a very, very little
Very
effect
little.
compared to.
Do you typically incorporate gravity into your calculations in high energy physics?
I'm sorry, say that again.
In high energy physics, do you typically incorporate gravity into your calculations?
No, I mean, they're still working on that grand unified theory, maybe in another 20 or 50 years.
Okay, fair
So
enough. All right,
for the most
so
part, they ignore it.
right. So in high energy physics, gravity doesn't matter. But in astronomy, gravity matters enormously. Heck, just at normal Newtonian on the surface of the Earth scales, gravity matters enormously. Aerospace engineering, there's so many great answers here. Space science, mechanical engineering. And here's a great answer. Thank you, Van. It matters in computational fluid dynamics, and it doesn't matter in computational fluid dynamics. It depends on the particulars of what you're doing. Geophysics, gravity matters. Biology, it matters, right? Um, Gravity doesn't matter a whole lot in optical science, right? Rocket science, right? There's a whole ton of these, right? Gravity matters where masses exist. Well, in high energy physics, masses exist. It's just that the particles are so small. I would say gravity matters where masses are massive, um, for a sufficiently small definition of massive, I suppose. But gravity doesn't matter where masses are tiny. I'm not saying it's zero. I'm saying it's not bigger than round off error, right? Okay, now rattle off some where gravity does not matter. And by the way, can you all plug these into the Google Doc as well? Give some examples where gravity does not matter. Math, good. Unless you're doing gravity calculations, but in most of math, that's not the case. Business, cell biology. Good, these are great, right? You can see where I'm going with this, right? So and this seems like such an odd question, but I'm using it as an example, right? To illustrate the idea. Digital humanities, language and literature, economics, right? I, I'm using this as an example to capture something important, that what we might think based on our own experience in our own discipline is super important when we're facilitating for a different discipline or a different subdiscipline or a different subdiscipline. That thing that's super important that we assume, because fish don't know they swim in water, that we assume is super important, may be completely meaningless, may be round off error, may be utterly irrelevant. Thank you. And please do make sure that these get captured in the Google Doc. All right, science versus engineering. What's the difference between science and engineering? Well, science focuses on discovery, learning something about reality. Engineering focuses on design. It leverages science, but it focuses on creating a new thing, right? And engineering is focused on constrained design, where the top two constraints are time and money. Now, in fact, those are the same constraint because, as we know, time is money. So the constrained design, the constraint on engineering is money. If you have unlimited money, you can engineer amazing things. In real life, you never have unlimited money. That's life, right? Okay. So that raises a question. Do engineers do research? That's interesting because some years ago, I was on the master's committee. In fact, was a co-advisor of a master's student in electrical engineering who was doing a master's thesis on some software. And the first question that my meteorology colleague on their committee had was, how is this research? They weren't poo-pooing the value of the work. They didn't understand that it was research. And I had to patiently explain the difference between science and engineering. So in engineering, you design a thing as a prototype of the engineering principles that you're studying, right? Do engineers do science research? So one of my colleagues in chemical engineering here studies flow through porous media as a way of understanding oil reservoirs and energy in general, hydrocarbons, right? So in his case, he's discovering about physical phenomena, very highly specific and focused physical phenomena. But maybe there's an argument to be made that he's doing science research, even though he's an engineer. I don't think he'd want me to say it that way. What about studying software? Is that research? Do computer scientists even do research? Right? I say this as a computer scientist. Have you ever been in a room where someone who is not a computer scientist refers to what the computer scientists do as IT? And there's a dead silence. You can hear a pin drop. And then one of the computer scientists, in a very specific tone of voice, patiently explains that what computer scientists do is not IT. Because to a computer science researcher, IT is the plumbing, right? Research is the grand glorified thing. IT is the plumbing, right? Wait a minute. Since when do computer scientists do research? What the heck is that? I thought they were just there to serve the needs of the real researchers, right? Have you ever been in that conversation? Oh, very uncomfortable conversation. Do not say that to a computer scientist. No, 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 no. They get that a lot and they're real tired of it. In fact, one of the problems that computer science researchers, one of the reputational problems they've developed with their non-CS colleagues, and why some of them have limited opportunities to collaborate with other disciplines, is because people in those other disciplines expect that the computer scientists will do something, perhaps create something potentially useful, write up a paper about it, publish it in a CS journal, and then abandon the project. Not make anything useful out of it, not follow through to make it valuable to the project. And I've seen it happen. So it's not universal by any means. I don't even know, I wouldn't even say it's the most common outcome, but it does absolutely happen. Right? Is simulated data actually data? So I had a colleague in chemical engineering some years ago, and we were working on something, and we were discussing, they were going to go to a conference and present whatever the results were. And I said, so when you're showing them the data, and he stopped me, he said, no, 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 no. I will not refer to this as data. This is simulated data. If I call it data, I will be laughed out of the discipline. Right? Computer science is more about designing and developing software and algorithms, with information technology is more about applying and managing those technologies in a business or organizational context. Yeah, I think that's a great way to express it, Kieran. I think that's spot on. But that distinction is not clear to people outside of computer science, or at least outside of CS and IT. Okay. A compiler designer thinks code is data, right? Everybody else thinks it's not data, but to a compiler or interpreter designer, that's data. So what would be some examples? And you can put this in the chat, and please also put it in the Google Doc so we preserve it. What are some examples of disciplines where the word data means something, let's say, more specific than a collection of ones and zeros? Star Trek. Okay, yeah. That's a character name, but I have actually had occasion to discuss the distinction between data and lore, and I don't mean the robot guys, I mean the actual things. My experience is lore is much more, resonates with people much more than data does. Every field, including your medical history, right? What are the disciplines that have unusual definitions of the word data? Now, here's the next question. Do the researchers you are working with know what you know? And here's the answer. No, they do not. Not even close. So the most normal thing in the world is to assume that everybody knows what you know. And the second most normal thing in the world is to be dead wrong about that. The problem is that once we know something, we just assume that everybody else knows what we know. I once met an HPC sysadmin who had only been an HPC sysadmin for a few months. Prior to that, they had been on an enterprise IT Unix team. And they had been pulled over to the HPC side out of necessity. And in 3 months, they had completely drunk the HPC Kool-Aid to the point where they could no longer imagine anything except research computing system administration. And the perspective that they had held mere months before was now completely alien to them. It was fascinating to me. Now, this is an extreme case of it, but we come to be engulfed by whatever is the normal understanding within our field. And we come to think of it as normal. And we just assume everybody knows what we know. How many of you have ever had an experience you're talking to someone in some discipline and they mention by name someone who's prominent in their field and you've never heard of that person and just goes right over your head? Have you had that experience?
Yes. Yes.
Right? But we all do it. We all do it. We assume people know what we know, but they don't. Got to tell them. People are really bad at this. I want to thank Bev Corwin, and she might be on today. I don't know. I want to thank Bev for pointing me to these two references, but they're really amazing. Even with something as simple as the concept of a penguin, you can't get people to agree what they are. And they did a study of this, and they found any two people selected at random, the probability that they will agree on what a penguin is 12%. 1 in 8 chance that they will agree what a penguin is. They can't even agree on when to stop talking. Only 2% of conversations ended when both parties wanted them to end. And only 30% ended when either party wanted them to end. Right? We're really, really bad at this. Okay, so here's an exercise, and you can do this as we go. I don't have to pause for you to do this, but go to the Google Doc, and at the bottom, there's a place to enter in terminology and say for a particular term, what's its meaning in specific disciplines or subdisciplines or sub-subdisciplines. Okay. What are unusual meanings of that term? That way, over time, and I think this is the third or fourth week we're doing this, it's on the web page. I'll put the web page URL. It's actually in the slides as well, but that's not very helpful. Let me put the URL here. Okay. Anywhere where you find the phrase Google Doc folder, just click on that and then double click on this talk. It should be listed as talk 02. Okay. And you can look at the time slot and you can look at the title. Okay. So go to the Google Doc and add more to it. We're building up a community understanding of terminology to share. Okay. Now, this came up in the last hour, and wow, I've already consumed 40% of my time or something. Nowhere near where I need to be, but we're having a great conversation, which is what's important. All right, so research computing versus enterprise IT. Are they natural enemies or natural allies? The first thing you need to know is that we are the weirdos, not them. Research computing is weird. The way we know it's weird is by its fraction of all computing. So enterprise IT is approximately everything that isn't research computing. So it's the campus network, it's the PC labs, it's the PCs, right? Desktop support. It's the tablet and phone support. It's classroom support. I mean, on and on and on, right? All of the things that you need to have a working institution that aren't research computing. At my institution, our fraction of central IT's budget, we're part of central IT. Our fraction of central IT's budget is about 6-7%. I don't know whether that's high. I think 1 to 10% is probably the norm for research computing versus enterprise IT. I think that's more or less normal. So I don't think we're way out on a limb. All right, so let's compare. What characterizes enterprise IT? How enterprise IT has to operate? The answer is 5 nines. And what that means is 99.999% uptime. That's 5.25 minutes of downtime per year. Okay. So in order to accomplish that, Everything has to be hardened. It's got to be secure. It's got to be established technology. It's got to be best practices. By the way, what does established technology mean to us in research computing? It means it's obsolete, right? You always have two choices in technology. You can have established technology, which means obsolete, or you can have new technology, which means broken. So on the research computing side, we're in the broken technology business. They send us the equipment pre-broken for our convenience, and then we work with the vendor to get it to work properly, right? So on the enterprise side, you've got to have the 5 nines. We'll talk about why in a few minutes. Okay. On the research computing side, this is characterized as 1.5 nines. And I'm not making that up. That is the official National Science Foundation standard. And I've quoted the text from, this is just the most recent. And supposedly in the next week or so, they're going to release the 2024 version of this. And I'll bet dollars to donuts it's going to have the exact same text in it. But since at least the mid-2000s, this has been the official NSF standard for getting on to 20 years now. The standard has been that the machines, the big machines they fund, which are typically 7, 8, even 9-figure machines, are allowed to be down for scheduled and unscheduled outages no more than 5% of the time, which means they're up 95% of the time. That's your 1.5 nines, right? We're going to talk about why in a little bit. So that means fast and flexible. You got to be able to turn on a dime. Tomorrow, we're going to get an email from some researcher who needs to do something that we've never done before. And he needs it yesterday. Fine, we'll do it. We may not get it done tomorrow, but we'll get it as quickly as possible. It's got to be cutting edge technology, which, as we talked about, means it's broken. As a general rule, there are no best practices. You know, the joke about research, if we knew what we were doing, it wouldn't be research. And every single research computing resource is a one-off. There's no factory pumping out supercomputers. That doesn't exist. Every single one of them is a one-off, right? There are no best practices. And by the way, what is 95% uptime? That is 18 and a quarter 24-hour days, 438 hours of downtime per year. Compared to, for enterprise, 5 nines, 5.25 minutes of downtime per year, right? That's what, 4 orders of magnitude difference, right? Well, that shouldn't surprise us, right? 3.5 orders of magnitude difference, I guess, right? Now, at OU, by the way, enterprise achieves about 4.5 nines, so that's about 30 minutes of downtime per year. And research achieves not quite 2 nines. We usually run at about 98.8% uptime. Okay, so why is this way? Well, the answer for both enterprise IT and research computing is money, right? So here's an example on the enterprise side. So in summer of 2016, so this is now what, 8 years ago, Delta had a power outage for 5 hours in their big data center in Atlanta. It cost them, by their own report, it cost them $150 million. That's $1 million of loss for every 2 minutes of downtime. Now, at my or your institution, it's probably not $1 million every 2 minutes because we have much smaller total revenue per year, total budget per year, but it's probably proportional. Okay. So let's say tomorrow is payday and tonight the payroll system goes down. What's going to happen? Heads will roll, or at least assistant heads, right? So in order to stay in business, in order to not be thrown out in the street to sell pencils out of a cup, in order to continue to be in enterprise IT, you have to lock everything down. You have to have those 5 nines, or you will be fired, period. On the other hand, on the research computing side, we don't have that problem. I'll talk about why in a minute. So we need to be cutting edge in order to be competitive, for example, for research funding. We need to have cutting edge capability. It's not that if we don't have cutting edge capability today, we'll be out of business tomorrow. But gradually over time, we'll become less and less useful. And eventually they'll say, well, what do we need them for? What do we need Henry for? He's not producing enough value. And I'll be on the street selling pencils out of a cup. Why is that the case on the research side? It's again about the money, but in a completely different way. So on the research side, let's say we're at a university and we have a supercomputer, and on any given day, on our supercomputer, we'll have 10 to 100 people running jobs, and they're from 5 to 50 different research teams. Yeah, when you live on the cutting edge, you bleed a lot. Absolutely. Right? Um, and I agree about not everything needs to be 5 nines. We're going to talk about that in just a moment. Um, and who does research computing at a university? Because most of us are at universities. Who does research computing at a university? Well, it's primarily grad students. There's some undergrads, there's some postdocs, and of course, staff and faculty too. But faculty mostly don't get to do research. Faculty mostly have to do research management, right? They get grants. They help the students learn how to do the research, how to write the papers, how to create the posters, all that kind of stuff. For the postdocs, they may also be teaching them how to write grant proposals, and they manage the team. That's their job, right? The researchers are mostly grad students. Well, what does a grad student cost? A grad student costs fully loaded with fringe and tuition support and overhead, because that's going to get charged the grant too. Fully loaded, you're talking 60-ish thousand a year, around figures. So it goes up and down depending what discipline you're talking about and so on. But 60K is probably a good enough guesstimate. So if there's a full 24-hour outage on a research computing system, what is the productivity loss associated with that? Well, worst case, there's 100 people on there. And to first order, most of them are grad students, right? Approximately all of them, but not literally all of them. So if you take 60K, divide it by 365, and then multiply by 100, you get about 16K of lost productivity. And that's, again, 5 to 50 different research teams. So you slice and dice that, and you find that the actual loss is between low 3 and low 4 figures per research team. And low 5 figures for the institution as a whole. Worst case. And even that's an exaggeration, because it's not that grad students only run jobs on the supercomputer. They're taking courses, they're writing papers. I mean, there's a whole bunch of stuff they're doing, right? They're taking training, all kinds of things that they're doing all the time. So if they have to sit on their hands for a day, that's not full loss of productivity. So the 16K is probably at least a third overstated, maybe double what it actually is, right? Maybe it's 8K, maybe it's 10. It's not a huge loss. Now, would they like to not have downtime? Absolutely. And I had this conversation once with a faculty member in front of my boss because I felt it would be useful for him to hear it straight from the horse's mouth. I said, as a physics faculty, I said, Pat, if I could offer you 5 nines, would you want that? You never have downtime, 5 minutes of downtime a year? Oh, yeah, that'd be great. I said, well, what if the cost of that was you'd have to give up 90% of your research productivity per year? He said, not if you live to be a million. See, the thing is, the budget doesn't go up when the cost goes up. And the cost of 5 nines versus 1.5 nines or 2 nines, this is not a knob you can turn. This is a toggle switch, right? It's either this or that. And the cost is about a factor of 10, maybe more, right? But it's at least a factor of 10, right? And my boss is not going to magically find 10 times as much money to give me, right? To go from 6.5% to 65% of his budget. It's not going to happen, right? That's laughable. So what I have to give up to have that level of reliability is I have to give up 90% of the capacity. Nobody wants that. And researchers are not measured on research productivity per day. They're measured on research productivity per year. They get an annual evaluation, right? So let the machine go down from time to time as a trade-off to get much more stuff at a lower price per unit of stuff. More compute capacity, more storage capacity, more speed, and so on, right? In exchange for a few lost days, it's not the end of the world. And it turns out that failure in research computing is totally normal. So this is the actual OU numbers from calendar year 23, right? We had 3.3 million jobs out of 3.9 million complete. We had about 300,000 fail in one way or another, right? So not quite 8%, not quite 1 in 12 jobs crashed for one reason or another. I don't mean ran out of time. I don't mean were canceled. I mean they genuinely crashed. right? But out of that 300,000, only about 13,000 failed because there was a problem on the server, and most of those weren't even hardware failures. So failure of a job is commonplace. Failure of the hardware the job was running on, failure of the job because the hardware had a problem is rare, extremely rare. So paying to have higher resiliency of the hardware doesn't make good economic sense. So what are the implications for IT? Well, research computing is cheaper than enterprise IT because it's 1.5 or 2 nines instead of 5 nines. But that's, of course, then it's 1.5 or 2 nines instead of 5 nines. It's less resilient, less reliable. So when a researcher comes to us and says, I want to do XYZ, one of our first questions is, can you handle about 8 hours of downtime per month on average? This is our 2 nines, right? If it was 1.5 nines, it would be, can you handle about 40 hours of downtime per month? But happily, we do a bit better than that. If they can handle that, then yeah, come to us. If they need to have it up all the time, no, go to the enterprise side, and you're going to pay a lot more. But it'll be worth it because you need to be up. You need your 5 nines, and they're going to deliver that. We will not, on purpose, we will not deliver 5 nines or even attempt to. With machine learning software, we're finding jobs crash nodes more often than in the past. Yeah, that wouldn't surprise me. Okay, now I mentioned this in the previous talk, but it's worth reiterating. In the olden days, 20 years ago, a new user would typically come to us from a PC background, right? Windows or Mac OS, laptop or desktop PC. But those were the olden days, and they're long gone. They're 20 years gone now. Nowadays, they come to us from from iOS or Android, right? From a phone, right? Or a tablet, right? Um, and that means that their sense of what computing is completely out of line with our reality, right? They think computing is tappity, 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 right? Not type a command at the keyboard, at the command line. That's completely alien to them. They have no notion of that, right? And it's a huge difference. So installing software, tap, 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 wants to open the store, wants to pick the app, and wants to give permission to listen to your phone calls. I get a lot of use out of that joke, right? But at large scale, what are you doing? Well, if you're lucky, it's an easy builder SPAC. But if it's not, you're going to be doing configure and make, and there's a bunch of dependencies that you have to download, and on and on and on. Most of our researchers have no idea how to do that. Right? At my institution, we provide the service. If they want us to install the software for them, we're happy to do it. Right? They have to get in a queue with everyone else. Usually we can deliver in a reasonable time. Right? Or if they want to install it in their home directory themselves and not wait for us, they're welcome to do that too. Right? But most users can't. They don't know how. Right? What about storage? Well, here on my phone, if I want storage, my phone happens to have an SD slot. So I pop out the little tray, I stick in an SD card, pop it back in, the phone immediately recognizes it, and I'm off to the races. Right? If I want a bigger one, I replace the small one with big one. I got to copy the files, but that's not a big deal. Right? That's all point and click. But at large scale, okay, so first you have to have a basic design, then you write an RFP. That by itself can take weeks or months, right? You put it out to bid, you have to have a bid evaluation, you then have to have a proper configuration of what you actually want to buy, then you do the purchase, then you have to deploy it, and then you maintain it over its lifetime. Maybe you expand it, maybe you don't. In the end, you decommission it. We're talking about months and in some cases years of labor. What's the cost? Handheld. If I want to pop in a card, $10 to $100, depending on the card. If my phone doesn't have a card slot, I buy a new phone. So that's what? Between $300 and $1,500, depending on how high end I want to go on the phone. Right? On a laptop, you're talking about tens or hundreds of dollars to get you like a USB drive, whether it's a spinning drive for high capacity or an SSD if it's lower capacity, but you want higher speed, right? What about at large scale? Tape, A petabyte of tape is going to cost you 5,000. That's pretty affordable at the institution scale, not the individual scale. You really don't want to have to buy a used car worth of money. Um, spinning disk, a petabyte of spinning disk is about 50K. So that's like a luxury car, not like the very highest end, but a pretty decent luxury car. A petabyte of SSD is about a third of a million. So that's like a nice, well, depending where you live. If you live in some communities, that's a bad house. If you live in my community, that's a pretty darn good house, right? And for large scale resources, petabytes, tens of petabytes, even hundreds of petabytes is totally normal, right? Why else is research computing hard? Well, we talked about the mindset gap. It's always getting harder to use, right? The storage hierarchy is deeper. The parallelism gets more hybrid. And then there's also more and more researchers using research computing, both more disciplines and more researchers per discipline. Enterprise compute applications tend to have interactive jobs and short-lived jobs. In research, a job can run for days. Are there not research cases in which days of productivity are lost? Yeah, absolutely. But days of productivity divided by total capacity is still a minor loss. Go back and look at the list of failed jobs. Most of our jobs are many hours, and I'd have to go back and run the numbers, but I suspect most of them are at least a day, and many of them are several days, multiple days. So yeah, absolutely. Also, a lot of codes have checkpointing built in where if the job fails, then when you can restart it, you're not restarting it from the beginning, you're restarting it from the most recent checkpoint, which is usually only a few hours of lost productivity other than the time when the machine was down. So you're not starting from the beginning again. Now, there are codes where you do have to start from the beginning, to be sure, but there are a lot where you don't. Okay. Now, why are researchers the way they are? So let's break them down. Okay, faculty, staff, students. Okay. So what are faculty rewarded for? And Bruce is going to talk about this in the early part of the afternoon after lunch. Faculty are basically rewarded for three things: bringing in grant money, publishing papers, graduating students. Now, depending on the institution type, that may have different priority order, right? If you're primarily a teaching institution, then graduating students is certainly going to be number one. Publishing is probably number two, and external funds is probably number three, in the sense that they will absolutely adore you if you do it, but it's not a requirement as such, or at least it's a gentler requirement. If you're at an R1, this is the order, right? If you're at an R2, I don't know exactly how that breaks out. Probably somewhat similar, although maybe publishing papers bubbles up a bit. The one thing faculty are not rewarded for at any institution that I'm aware of is having good IT. So are they going to spend their hard-earned money on good IT? No, of course not. Let's take a secret ballot. No, they're not going to spend their hard-earned money on good IT. They will spend the absolute minimum they can get away with, and they will scream bloody murder that the institution is not providing all the IT they need for free. Right? I'm faculty, so I know how this works. Among other things, I'm faculty. All right. Also, their mental model for what compute and storage ought to cost, if it's not going to be free, then it ought to cost what they paid for it at a big box store like Walmart, right? So what's the cost of storage? Well, I went over to Walmart and I got a 16 terabyte spinning drive, and it was about $25 per usable terabyte. So that's what storage ought to cost, right? That is not a realistic number at large scale, but they want the numbers to be as low as possible. If you're tenure track but not yet tenured, then your incentive structure is, I got to publish a bunch of papers, I got to bring in a bunch of grant money, I got to graduate a lot of students, because if I don't do that, I'm literally fired. At the end of my tenure process, I will not get tenure, and I'll be out on the street selling pencils out of a cup, right? I'm always amused by listening to new faculty tell me all the things they fervently believe that overhead covers. Yeah, no such luck, huh? The need, everything has to work right now without interruption, because I have a very limited timeline to do everything it takes to get tenure. You know, they say tenure is 7 years, and that's true. But year 7 is your gap year. If you didn't get tenure, that's your year where, there's not enough demand for pencils out of a cup on the street. It's the year when you are looking for a new position because you didn't get tenure. So you got 6 years, but year 6 is when they're deciding whether to give you tenure. So you got 5 years, but it takes half a year to go from submitting the journal article to getting it published. And most disciplines, what matters is journal articles, very much not conference papers. There are disciplines where conference matters, mine included. Computer science, conference papers do matter quite a bit. But there are a lot of disciplines where conference papers matter very little. What matters is journal articles, right? And it takes up to 6 months. In fact, 6 months is common to get a paper from first submission to accepted. And if it's not accepted, it's not going to be counted toward tenure, at least not that much, right? So I've got 4.5 years to do all the research I'm going to do to get tenure. Okay. Yeah, in some disciplines, 6 months is optimistic, grotesquely optimistic in some cases. All right, what if I've got tenure? Well, we already know the incentive structure, and by now I've got 7 years of habit, right? That I got to do this and do this and do this. So the mindset doesn't really change that much. Plus, I want to get raises. I want to get promoted from associate professor to full professor, which, by the way, comes with a raise. I want to get a named chair. I want to get elected to the national academies. I want to get prestigious awards from my colleagues around the world, right? Recognition. All of that improves my standing locally as well as nationally and worldwide. So I need stuff to work now, and it's got to work all the time, right? Just the same as when I was on tenure track. What about non-tenure track faculty? Well, if I don't bring in the grant money, then there's nothing to pay my salary. If I'm a research professor, research assistant professor, research associate professor, whatever, I have to find my own money to pay my salary. The institution does not take responsibility for my salary. So if I'm going to do that, then I need to make sure that I'm bringing in the grant money. Otherwise, I'm out of a job. I'm selling pencils out of a cup on the street again, right? I got to publish a lot in order to bring in the grant money. And I have to have a track record of graduating a lot of students so that someday I can get a tenure track job somewhere, because I don't want to live on soft money forever. Living on soft money sucks because you never know if someday, maybe next year or next month or next week, you're not going to be able to eat and your family will starve in the dark, right? Soft money sucks. The only thing worse than being on soft money is not being on money at all. So everything has to work all the time. Right? What if I'm a postdoc? Well, I got to publish a lot, otherwise I won't get to continue to be a postdoc. And I ultimately want to become faculty, probably. That's why I'm bothering to do a postdoc in most cases, or at least in many cases. So I need to learn how to get grant money, and I need to publish a lot of papers so that I can go get a permanent position, or at least a research faculty position. That would be nice, right? Postdoc, you do 1, 2, sometimes you hear of people doing 3 postdocs. And then if you haven't secured some kind of longer term position, you're going to be in trouble. What are the university retention requirements for data results for PhD and research papers? How long in years, and who pays for it? That is an excellent question that nobody has a good answer for. I've got a whole talk on that, which will not be part of this workshop. How about if you're a student? Well, your number one goal as a student is to graduate, right? Because you're losing time and money. I calculated that the dollar cost just of foregone salary and fringe benefits of being a grad student for me was between $250,000 and $500,000. Now, I make a better salary now than I would have if I didn't have the graduate degree, to be sure. But it took a long time to catch up, right? Anything that delays my graduation is costing me money, especially if I don't have an assistantship or a scholarship or whatever. And as I said, I'm giving up. I'm foregoing salary and benefits in a full-time position. Okay, let's talk about research funding, because that feeds into all of this. What's the academic research funding model? Grants. No, yes, contracts, cooperative agreements, and so on and so forth. They're all pretty similar in this context. They all really turn out to be a random amount of money that shows up on a random date and is available for a random duration, right? 3 years is typical. I mean, more broadly, 2 to 5. You occasionally see 10-year grants, but that's not common. There's a disconnect between one-time grant funding and ongoing subscription models that most computing resources use. That is exactly correct. And at our institution, the way we address that is not doing recurring charges, doing one-time charges. Okay. And by the way, it's not perfect one-time charges, but it's only occasional charges. Grants strongly favor researcher salary and fringe and indirect, disfavor anything else, especially equipment and services, just as you say. And even if they were to favor services, well, if you've got a 3-year grant and you put a bunch of data in a commercial cloud, in month 37, they will cheerfully delete all your data for you because you stop paying. And the thing is, you can't start paying for that on the next grant because the next grant probably is not about the same stuff and doesn't use that data. Right? So researchers don't get a lot of credit for buying equipment and services and paying for non-researcher staff, and they don't have the ability, as a general rule, to pay recurring charges long term. There is internally funded academic research. So some institutions use part of their endowment proceeds to pay for some of the research that their faculty do. That generally only happens at high-ranked institutions that have large endowments. So the problem with the top 50 is there's only 50 of them, right? Most of us are not at those institutions. Okay. If you write a grant proposal, what's your probability of success? So, sorry, that should say federal fiscal year 23. 29% success rate at the NSF overall. I'm picking on the NSF because I know what the URL is to find the information. If you break it down by directorate, by discipline category, it varies quite a bit. Geosciences is at 44%, biosciences is at 24%, social, behavioral, and economic is 23%, right? I'm not sure what causes the disparity. It may simply be that there are a higher fraction of researchers in, for example, biosciences. In the case of social, behavioral, and economic, a big contributing factor is they get a very small budget each year compared to the other directorates. Okay. Where they buy it and central IT decides the service should not be used, such as Dropbox. Yeah, that does happen too, for sure. NIH success rates are closer to 10 to 12%, depending on the institute. Yeah. So this is just one example. By the way, that 29% is up several points. It used to be worse than that. If you break it down by state, you can see an even broader range, right? So Guam only submitted 3 proposals in fiscal year 23, and only one of them was funded. On the other hand, if you look at, for example, Hawaii, their success rate is 43%, and at the far end, Kentucky and Louisiana are at 22%. These are EPSCoR jurisdictions. If you look at non-EPSCoR, Florida is 23%, but Minnesota is 37%. So you can see there's quite a disparity by state. But no matter what the success rate is in your state or in your discipline, none of that matters. What really matters is you have to submit a lot of grant proposals to get any money. You spend a lot of your time submitting grant proposals. At my institution, one of the strategies that we adopted was we don't have researchers submit proposals to use our machines because they have a certain number of hours per year that they can devote to writing proposals, and we'd rather that they spend that time getting somebody else's money than writing proposals to use stuff we've already bought. Okay. So most academic institutions fund research by a combination of internal funds on some kind of regular cadence, fund research computing, internal funds on some sort of regular cadence, like an annual budget, or at random times, like, oh, it's been 5 years, let's buy a new supercomputer. Or grant funds, which are always at random times, like let's write an MRI or a CC Star compute to buy a supercomputer or a DoD DURIP. For public institutions, you might get state appropriations. They're probably random. It can happen that you get a state budget line. It's not that common. The problem is that the legislature giveth and the legislature taketh away. So if they're giving you some money and then they come back and say, oh, well, it's a tough budget year this year, so you're the obvious first ones to cut. then you're in trouble because then you have to lay off all your staff and you don't have research computing, even if the machines are still there, right? Usage charges, this is not common at all. It's very uncommon to have usage charges. Maybe 15 or 20% of academic research computing organizations charge usage charges. And here I don't mean like premium charges for premium service, but just for the regular service. That's very unusual. And if they do, they often say you get this much for free and then you have to pay. Right. So how should faculty spend their time? I mentioned this about we don't ask them to write grant proposals to use our machine because we'd rather they get money with that time. Okay, so how do we talk to researchers? Here's things you can say that will make you very popular. Here's another way to do this thing you're trying to do that's going to be cheaper than the way you're trying to do it. Oh, they love that. Or here's another way to do it. It's the same cost, but here's how much better the outcome will be, right? They love that. Cheaper, they like cheaper more than they like more outcome for the same money, but either one will do, right? Control. You get to decide how you use the thing you paid for, right? We're not going to impose on you how to do it. You can share it with whoever you want, including your colleagues outside of our institution. This is very, very popular. They would much rather people come to them and use their computing resources than go to the other institution and use the other institution's resources. Your students won't have to waste their precious research time managing machines. They like hearing that, right? We'll put IT professionals on managing your machines. Your students can focus on doing their research. That'll be more productivity, more papers for you from your students. So they love, this is what stuff that researchers love hearing. All right, now how do you find the researchers? Where are they? Where are the computing and data intensive researchers located? Well, the answer is they're on your institution's website. So you go there, and almost every academic institution website has a link right on the homepage that says academics. So click on that, find the department websites, and then each of those department websites find the list of faculty. And usually that just says faculty or people or something along those lines, right? And then go read their research descriptions and look for keywords and phrases. So look for computational, numerical, parallel. That one shows up a lot in CS. Informatics. In chemistry, there are computational chemists nowadays, didn't used to be, but also look at physical chemists and biochemists, right? In chemistry, look for the word calculation, right? That's their term of art. There's lots of other buzzwords like this. Over time, you get a feel for it. Numerical shows up a lot in engineering. That's typically where you'd expect to find that word. Computational, you're more likely to see in physical sciences. So now you've identified those faculty. What do? You contact them, right? Send them an email. Tell them what your role is. If you're working on a proposal, tell them what program you're writing to, what's the due date, how much money it is, and what it's going to accomplish, what the purpose is. And ask them what kind of computing and storage and network and so on, what kind of needs do they have? Go to meet and greets. So most institutions have faculty meet and greets. They were obviously a lot more popular before COVID, but they came back after COVID. So if your institution has events like that, and some institutions may have them on Zoom or whatever online, but go to those events. Get 5 minutes. Ask the event organizer, can I have 5 minutes to present about what we're doing? Right? And then pass out your business card. Or if you have an info sheet, like a piece of paper that describes what your capabilities are, that can help, and has your contact information and so on. Visit them. Make an appointment. Even better, take them out to lunch. Right? Oh, there's so few people who, if you offer to take them to lunch, they'll say no. Very few people will turn down a free lunch, even knowing in the back of their mind that there ain't no such thing as a free lunch. And find out what is it that they're working on and what do they value that research computing can help with, right? At a high level, what's your research about? What are the computing and data intensive aspects? And this is one of my favorite thought experiments to do with researchers, especially faculty, because faculty generally operate with a sense of scarcity. What can I accomplish with the minimal amount of stuff? Because that's all I'm going to get anyway, So ask them the opposite question, because it's probably a question they've never thought about. If I could give you an infinitely large, infinitely fast supercomputer, what would you do with it? How would that differ from what you're doing now? And I'm always upfront with them. I'm not going to ever offer you that. But if we start from there and work our way back, we'll get a better outcome. All right. So here's that exercise that we had before about the glossary of terminology on the Google Doc page. So make sure you contribute to that. I think that's going to be very, very valuable. And you can see some of the stuff from the past couple of years, and all of that is very helpful. All right, so we have about 5.5 minutes for questions. So what questions can I answer? And you can use chat or voice. And I will give a crisp dollar bill the next time I see you in person if you ask the first question. Good. Eric, so you can now hold me to this. The next time we see each other in person, I owe you a crisp $1 bill. So what is EPSCoR? So EPSCoR is now the established program for the stimulation of competitive research, formerly experimental. It was experimental for about 30 years, and then it became established. Sean, I'll get to you next. Good. And in fact, well, all right. So EPSCoR, the theory behind EPSCoR is there are states that don't get their fair share of federal research funding, however you want to define that. The way EPSCoR defines it is 0.75% of federal research funding. So if all states got the same, which would be ridiculous because of differences in population and so on, but if all states got the same, then every state would get about 2%. It's actually a little less than that because of territories. So, but call it 2%. So the cutoff for being an EPSCoR jurisdiction, state or territory, is your state or territory gets less than 0.75%, 0.75% of federal research funding. If you are in an EPSCoR jurisdiction, you get some legs up. One is they will cheerfully send people to your state or territory to do training on how to write grant proposals. They're happy to do that. Number two, most of the federal research funding agencies have specific programs that are only open to EPSCoR jurisdictions. They're called EPSCoR in NSF, NASA, DOE, DOD, sorry, Department of Energy, Department of Defense. I don't know if NOAA does this, the National Oceanographic and Atmospheric Administration. I don't know if they have an EPSCoR program, but and then the National Institutes of Health call it INBRE, I think, but it's basically the same thing. So these are specific program solicitations that are only open to EPSCoR jurisdictions. And then the third thing is if a proposal whose lead institution is in an EPSCoR jurisdiction, if that is ranked as competitive but not highly competitive, the program officer can go to that funding agency's EPSCoR office and say, will you go halvesies on this with me? Where some of the money will come from the EPSCoR office and some of the money will come from the program that was submitted to. I was at the NSF EPSCoR workshop on Monday of Tuesday of this week. A group of states is short by 300 proposals this year. They are begging for proposals. Yeah, I try to submit some every year, but I don't have a perfect track record. Okay, so that's EPSCoR. So then let me turn to Sean, who had the next question.
Yeah, hi Henry. Based on this what you're saying about researchers, faculty not being rewarded for cyber infrastructure, the purchase of and all that, and the fact that there's now access, what used to be Exceed and the big kind of publicly funded supercomputers. Is there a real penalty on trying to get funding for center-owned HPC systems, anything like that?
No, and it comes down to do the national centers have the same mission as the institutional centers? And the answer is they do not. I would characterize the mission of the national centers as big we and weird. So if you have a problem that's too big to run at your local institutional research computing center. So at our center, we have about 30,000 cores and I think on the order of 30 terabytes of RAM, and we're into we're into 2 figures of petabytes of disk. And we have room to grow into 3 figures of petabytes of tape. So if your problem will not fit there, we got people at my institution who they can't fit their problems on our machine. Can't do it. National centers, so the Texas Advanced Computing Center, the National Center for Supercomputing Applications at the University of Illinois Urbana-Champaign, the Pittsburgh Supercomputing Center, the San Diego Supercomputer Center. These are the NSF-funded national supercomputing centers. There are also Department of Energy-funded national supercomputing centers like at Oak Ridge, Lawrence Berkeley Lab, Lawrence Livermore Lab, so the National Energy Research Scientific Computing Center, or NERSC, is an example of this. Most of the big DOE labs have national supercomputing centers. Then there's the HPC modernization program in the Department of Defense, and they run a bunch of national supercomputing centers. But the national supercomputing centers have a different mission. The national supercomputing centers focus on problems that are too large to run at your local institutions that are too small to have local resources. That's the we part. And then machines that most institutions couldn't afford to have locally because the amount of uptake of them at the institution scale is too low to justify the cost. So, for example, a big shared memory machine. Very, very difficult to justify spending the money it would take to have a 16 terabyte shared memory machine at an individual institution. But you can do that at a national center because the national demand for such a thing would be enough to justify the expenditure. So national centers are a very important part of the picture, but they're not all of the picture. And the proof of that, the institutional centers are the middle part of it, but the proof that you do need the institutional centers in addition to the national centers is the difference in headcount. So the national centers, and in particular the access centers, formerly known as Exceed, these are the NSF-funded national supercomputing centers, they have on the order of 10,000 users. The institutional centers collectively have on the order of 100,000 users. And that's how we know that they have a different mission, because they're serving different constituencies. Now, the constituencies absolutely do overlap. So one of our biggest users here is also in the top 50 biggest users at the NSF-funded national supercomputing centers. But they're doing different things there than they are here, and in different ways. Did that answer your question, Sean?
Yeah, Henry, thank you so much. That was exactly what I was looking for.
Happy to help. What's next? I love questions. I spent my crisp dollar on Eric, but I'll put another one up. By the way, Eric, it's on you to remind me if you see me. I'm putting a second crisp dollar bill into the pot here. Who wants to ask a question and be owed a crisp $1 bill? No, you didn't. You made the mistake of diving in and asking the question before I was begging for questions. It's like when the ticket agent says, "Okay, we'll give you $200 if you take a different flight," and then you take the $200, and then like 10 minutes later they're saying, "Oh, we'll give you $1,000," and you already got your $200, and that's all you're gonna get. Thoughts about pros and cons of different cost models, chargeback, institution pays all of it, etc. I've got a million thoughts about that. In the end, I believe that the charging model has to align with A, how research is funded, and B, what the local conditions at your institution are in terms of the researcher's ability to pay for access to those resources. So at our institution, researchers are not guaranteed to always have giant piles of money. I have a colleague slash friend who spent a lot of his career in an EPSCoR state at an R1 institution, but an institution that did not have a lot of money. Very low on the totem pole in terms of annual research expenditure. And then he moved to a top 25 institution, and he was at that institution for several years. And I asked him about that, and he said the difference was night and day. That at the old institution, he never had enough money. At the what was then his current institution, he literally had more money than he knew what to do with. He was turning down projects that were being offered to him. And the reason was, for any given principal investigator, there is a limited number of people that they can effectively manage before it starts breaking down and they can't manage people properly anymore. Let's say that number is 10. At my institution, a typical faculty member is going to have 1 to 5, let's say 3 grad students and postdocs, usually grad students, right? So any additional money they get has to be spent on more grad students in order to maximize that faculty's research productivity. But in an institution that's overflowing with money, they can't hire more students and postdocs and so on because they can't manage them properly anymore. They run out of hours in the day to meet with their students and postdocs. So at that point, spending their money on things that make each of the students and postdocs more productive, instead of spending their money on hiring more students and postdocs, when you're flush with money, make each individual maximally productive. When you're broke, hire more individuals. That's an important part of what's the right solution. Align it with the research funding model and align it with the institutional circumstances. If your institution is flat broke, if your annual research expenditure is $10 million, you are not going to be charging your faculty's grants for core hours because they ain't got it, right? But if your institution's annual research expenditure is $1 billion, yeah, knock yourself out. They won't even notice it. Right? So it depends on the particulars of the institution. Okay. What is the difference between NRP and Exceed and Nautilus, etc.? Oh boy. So tomorrow morning's talk is called the Cyber Infrastructure Landscape, and at least some of that will be covered in that talk. 75 minutes will not be enough to do all of that justice. Exceed is now defunct. It has been succeeded by Access, and Mike's going to talk about that tomorrow morning. So I'm going to table that question because a lot of that will get discussed tomorrow. I don't know if he's going to talk about the National Research Platform or not. That's more of a networking issue. Okay, how many users will justify? Oh, hang on, I'm jumping around a bit here. About how many users will justify an NSF-funded regional supercomputing center? Are there NSF-funded regional supercomputing centers? They're mostly national. Usually, if they're going to put up that kind of money, they expect you to be open to all comers. I'm not specifically aware of a regional one. Are there any regional ones? The Texas Advanced Computing Center does provide some additional capabilities specifically to Texas, but I'm not aware that they have a mandate, for example, to cover Oklahoma and Louisiana in a particularly extra way compared to how they do for New York or Oregon, right? I'm at least not aware of such a thing. So I don't think there is such a thing as regional. I think they decide national. If I'm wrong, let me know. That's a new one on me. Okay. My institution has noticed a growing problem with users who do not want to invest time and resources in checkpointing and or creating code to run reasonably on fair share compute resources. Do you have any tips for talking to users like this? No. And the reason is they don't write their code. The overwhelming majority of our users do not write their code. Or if they do, they're writing a Python wrapper around TensorFlow, and where the time is being spent is in the TensorFlow calls. It's not in the wrapper script that they wrote. So we could try to solve that problem, but it would have only an incremental improvement. Now, if somebody's running code that could be checkpointing and they're not, and we notice that, we can help them get the checkpointing going. I've never had a user be like, oh, I'm not going to do checkpointing. Checkpointing sucks. I've never heard a user, maybe users say that. I've never had that. I've never encountered that. But I haven't seen many cases. So usually when our users write their own code, they are doing very small things. They're running on a single node, maybe even a single core or a few cores. They're not consuming a ton of RAM usually. If they're doing something large scale, they almost always didn't write the code themselves. And if they did write the code, it was they were part of a national community model that they're not the only ones writing the code, and they have to follow certain guidelines to get good performance and to have good practices. So we have a couple of groups like that at my institution. And then we have a bunch of groups where there's a few people writing little bits of code, but they're not doing big stuff as a general rule. So I don't have a good answer for that, I suppose. UC Merced is developing a Central Valley one in California. Is that being funded primarily by federal funding agencies or by the state?
NSF, it's a CC Star grant.
Okay. So the CC Star grants, yes, but the dollar figures on those regional CC Star computes are not big enough to create a center. They're big enough to buy what for a large number of institutions is going to be a pretty modest shared resource. I think those budgets are typically high 6 or low 7 figures. It's not going to be like a big national center or even, an order of magnitude down from that as a general rule.
Well, no, but you were asking about regional centers, and it is one that we're working on developing. So that way the CSUs in the Central Valley have access to those compute resources we don't normally have.
And that there's also some encouragement to do that, for example, under the Major Research Instrumentation Program that the NSF runs. So, for example, in Oklahoma, there was a $4 million MRI grant, and that's, I think, as much as you can request on an MRI for a machine that would be available to Oklahoma, Arkansas, and Kansas. And in fact, the acronym for it is OAK, O-A-K. That's not a regional center. That's merely a regional resource. The center is institutional. How do you price ongoing support costs for, hang on, sorry, my chat is running around. How do you price ongoing support costs for one-time charges, e.g. HPC buy-in? Right. So the way that we've historically done it is we look at the aggregate cost of the hardware and then divide by the number of units. Can we ask those who want to write NSF proposals to do a meetup in a follow-on meeting? So we actually have some talks on how to write NSF proposals to get equipment. So if there's interest in that, send me an email and we can schedule something and make it available nationally, and anybody who wants to sit in on it is welcome to. I've already got slides for that. So if someone wants us to do that, just send an email. I would also recommend at some point we probably should do a session on how to be a grant proposal reviewer, because the best way to improve your grant proposal writing skills is to see the wretched grant proposals that other people write and also the fantastic ones that actually get funded, because then you get a really good feel for what helps a grant proposal be successful. And I should tell you, just Friday, I think it was, I got some on a grant proposal that I was on. We got some of the worst reviews I've ever gotten in my life, and it doesn't stop me at all. What I immediately thought was, okay, great. So now I'm going to make it my business to learn from the reviewer complaints, and next year we'll write a better one. Because I think the next one's going to be due in January. So we'll just write a better one. The fact that this one failed and got terrible, terrible reviews does not bother me in the slightest. I mean, would I have liked it to get funded? Sure, of course, but that's not how life works. Sometimes you get dinged. And so we'll just do better, and maybe it takes a couple of iterations before we get it. That's fine. Do you encourage new faculty to use startup funds to buy into an HPC, the condo model? It depends on what their needs are. I don't encourage anyone to do anything on general principle. I encourage them to tell me what it is they're doing, how they do it, what their needs are, and then see whether what we offer is a good fit and how we can get them the best outcome. It's very researcher dependent. So if they come in and there's a valid need why they would need condominium resources, dedicated resources as part of their work, and for many of them that's the case. Absolutely. And I'll give them a sense of what it's going to cost and what the implications are, and they will go into their startup package negotiation with, I need the following things. And typically they'll get that or at least something pretty close to it. But because I think by this point, the chairs do trust us to understand what is and what is not needed and what's the most cost-effective way to do it. So, yeah, I would say there are faculty candidates who we do encourage to do that, and there are faculty candidates who we don't encourage to do that because it's not the best use of their money. Bigger proposals need a network of researchers for NSF. Phil, are you talking about for reviewing? Because what I would say is, in our case, bigger proposals need a network of research computing professionals for the NSF to draw on to do reviews. Because one of the risks is that someone writes a research computing proposal instead of a research proposal, but gets reviewed by researchers. And in fact, the sifted proposal went through 2 iterations of that before it got funded on the 3rd iteration. And a big part of the issue was the people who were reading it, at least some of them, were computer science faculty, and they came in with a set of assumptions that simply that were not relevant to cyber infrastructure professionals. And so we had to rewrite the proposal in a way that would prevent them from getting wrong ideas into their head at the beginning. Because you've noticed, I'm sure everybody has friends and relations and colleagues who, once they get a wrong idea in their head, there's no hope of pulling it back out. And this was clearly what was happening. And so we had to restructure the proposal to some extent so that the right ideas were right up at the front. The things they were going to misunderstand were explained properly right up at the front. So there was no possibility of them starting with a wrong idea. And it was very labor intensive to figure out how to do that. So those of you who participated in the grant proposal writing apprenticeship, I think you all got a lot out of going through those multiple iterations to figure out, how do we say it in a way that CS faculty will understand? And I say that as a partial CS faculty myself. And we had to kind of crawl around inside their heads to understand and to predict how would they react to certain ways of saying things. Good. More questions?
Henry, the NSF new scheme, they have a 10-year, $100 million proposal thing. So you can't spend 10 million a year at one university. You're going to have a collaborative group of 6, 8, 10 universities and 1 or 2 lead universities and some. It's going to take a team to get some of those new research proposal ideas that they have.
Yeah, absolutely. Okay? Yeah, and I mean, so they've had programs like that for a while, but typically, in most cases, and this is by no means universal, there have absolutely been exceptions to this, but in most cases, the research computing part of the project is one small piece, and the bulk of the project is focused on the STEM research question. But there are absolutely projects where you can have a large-scale center or resource that is available nationally. You do not typically get funded for a large-scale resource for regional. All right, well, we're a bit past our time, so I don't want to abuse the privilege. So our next session starts in just under an hour and a quarter, so about an hour and 12 minutes. So half past, so it's 2:30 Eastern, 1:30 Central, 12:30 Mountain, 11:30 a.m. Pacific. I think Hawaii time is 2 hours before Pacific. Is that right? I can't remember. Anyway, you all can calculate it. But about an hour and 12 minutes, or by now, an hour and 11 minutes from now, we'll be starting with our next session, which is Professor Bruce Mason from OU. We'll be talking about what it's like to be faculty and how to communicate with and work with faculty and understanding faculty so that you can be more effective when you are collaborating with them. And I'm going to go ahead and stop the recording